Good morning, students. Next, we are going to discuss about mean value theorems, basic theorem, and then Rolle's theorem. In the next class, we are going to discuss about mean value theorems. Right? This is Rolle's theorem and basic introduction theorem. That's it. Right? Now, mean value theorems. Right? Introduction. Suppose one function is given to you, right? You have to you have to find the maxima or minima of the function in a given open interval f of a comma b. Then how to find the maxima or minima? If maxima or minima exists for the function or not, right? What are the conditions? To find the maxima and minima of a continuous function f on an open interval or closed interval a comma b, it suffices to consider the points x where f dash x is equal to 0. That means the differentiation of x at a point x is equal to the value of the first order differentiation is equal to 0. The points where f is not differentiable and the end points a and b. See, the closed interval is given to you. See, now suppose if the closed interval is 1 comma 2, right? First of all, we have to find f of 1 value and f of 2 value, and an x lies between 1 and 2. That means 1 less than or equal to x less than or equal to 2. X lies in between 1 and 2. We have to find f dash of x. If f dash of x is equal to 0, then we can analyze the given function whether f has minimum or maximum. Right? If f dash of x is not equal to 0, if f dash is not differentiable, and we have to calculate the function value at the end points. Now, see, once again, to find the maxima and minima of a continuous function f on an open interval closed interval a comma b, now it suffices to consider the points x where f dash x is equal to 0. Right? We have to search for the values of x in between a and b such that f dash of x is equal to 0 and the points where f is not differentiable and the end points a and b. That means we have to find f of a and f of b because a and b are the end points of given interval. Now, theorem. If f is defined on an open interval containing x naught, if f assumes its maximum or minimum at x naught, and if f is differentiable at x naught, then f dash of x is equal to 0. Right? This is the given data. Once again, you have to read the statement. Now, f is defined on an open interval a comma b containing x naught. Right? That means x naught lies in between and the open interval. If f assumes its maximum, you can assume maximum or minimum at x naught. That means f of x naught is greater than 0 or f of x is less than 0, or minus f of x naught is greater than 0 minus f of x naught is less than 0. And if f is differentiable at x naught, then f dash of x is always equal to 0. Now, once again, we are writing the given data. F is defined in an open interval containing x naught. Let the open interval be, we don't know that open interval we are taking as a comma b. Here x is given as lies in between a and b. That means a less than or equal to x or less than or equal to b. X naught, no? X naught, that way I am writing. Now, since f r minus f, see, that function may be negative or positive. F has maximum, then minus f has a minimum. If f has a minimum, then minus f has a maximum, right? Assumes its maximum at x naught. We are assuming that at x is equal to x naught, the function f or minus f have maximum value. Assume that f assumes its maximum at x naught, that is f dash of x greater than 0. right? Now, since what is f dash of x naught? See, we know that what is f dash of a? F dash of a means differentiation of f at x is equal to a, no? That means limit x tends to a, f of x minus f of a by x minus a. This is the definition of differentiation, right? Suppose if you want to find f dash of y, then what you will write? As x tends to or y tends to, this is a, no? That, right? X tends to y, f of x minus f of y by, now what you will write? X minus y. This is the definition. Similarly, f dash of x naught. What is the definition of this one? Limit x tends to x naught, f of x minus f of x naught by x minus x naught. This is the definition of differentiation at x is equal to x naught. This is the standard definition of f dash of x at x is equal to a, right? Now, similarly, here f dash of x naught I am writing. I am using the standard definition. Limit x tends to, instead of a I am writing x naught, right? Now, f of x minus f of a I have to write, but a value instead of a here the value is x naught. That's why I am writing x naught by x minus x naught. That is the basic definition of differentiation. Now, again, for this differentiation, there exists delta greater than 0 such that a less than or equal to less than x minus delta less than x plus delta less than b. This is obvious. Suppose if the open interval is 1 comma 2. Suppose if you take an x value here 1.5, 1 less than 1.5 less than 2, no, obviously. Now 1 less than 1.5 minus 1.5 minus 0.1 less than 1.5 plus 0.1 less than 2, which is true or not? Yes. Say this is 1.5 minus 0.1 means 1.4, 1.5 plus 0.1 means 1.6. Both the values lies in between 1 and 2. Here this is x naught, this is delta less than x naught plus delta, which is obvious, no? Right. And 0 less than or equal to mod of x minus x naught less than delta implies this value is greater than 0. For this value is always greater than 0. You call that equation number 1 because that x naught lies in between a and b, right? Now, we have to select x so that x naught less than x naught plus delta. We can choose point from these two. That means we can choose the points 1.5 between 1.6, right? 1.5 means x naught plus delta, I told you, no? X naught means 1.5. We can find the numbers in between these two, no? That means 1.55, 1.51, 1.52, 1.53, 1.555, 1.522, like that. Infinite number of points will be there. Now then, f of x naught is greater than f of x naught or not? Yes, which is a contrary assumption that f assumes its maximum at x naught. Our assumption is what? Our assumption is f assumes that its maximum at x naught. That means f dash of x greater than 0. F has the maximum value at x naught only. But here we are getting f of x greater than f of x naught. That means which is a contradiction, right? Now, likewise, see, continue this process. Likewise, if f dash of less than 0, if f dash of x less than 0, what will happen? There exists delta greater than 0 such that 0 less than mod x minus x naught less than delta implies f of x minus f of x naught by x minus x naught less than 0. If it is less than 0, then this value is also less than 0. If we select x such that x naught minus delta and x naught, Now we have to choose x value between these two. Then from equation 2, f of x greater than f of x naught, which is again a contradiction. Therefore, f dash of x is not greater than 0, f dash of x is not less than 0. If it is less than 0, we are getting a contradiction. If it is greater than 0, we are getting a contradiction. Therefore, f dash of x must be equal to 0. Right? Please go through this theorem step by step. Next one is Rolle's theorem. Very important theorem. Rolle's theorem and mean value theorems are very important. You will get the problems on Rolle's theorem and also the theorems. Rolle's mean value theorem and mean value theorem. These two are very important. Now see, let f be they'll ask the question like this: state and prove Rolle's theorem. State and prove Rolle's theorem. The statement, let f be a continuous function on closed interval a comma b, and it is differentiable on open interval a comma b, and f satisfies f of a is equal to f of b, then there exists at least one value of x, say x, in between a and b, such that f dash of x is equal to 0. Right? Or you can say there exists at least one value which is lies in between a and b, say c, such that f dash of c is equal to 0. Right? What is the statement? F is a continuous function on closed interval a comma b, f is a differentiable on open interval a comma b, and f of a is equal to f of b. This is very important conditions in Rolle's theorem. If f of a is not equal to f of b, then Rolle's theorem cannot be applied. Remember, right? If f of a is equal to f of b, then only Rolle's theorem can be applied. Otherwise, we cannot apply Rolle's theorem. Now, see proof. What is the given data? F is a continuous function on closed interval a b, f is a differentiable on open interval a comma b, and f of a is equal to f of b. This is the given data. Now what is our aim? Our aim is to prove that f dash of x is equal to 0 for x belongs to a b, open interval a comma b. That means x lies in between a and b. Right? Now case 1. Suppose if f of x is equal to 0. Assume that f of x value is 0. Then there is nothing to prove, since f dash x is always 0, no? Right? Now, then for a and x in b will be such that f dash of x is equal to 0, and hence the theorem is proved. If the function is equal to 0, then its derivative is also 0, no? Right? Now, you suppose if f of x is not equal to 0, for any x belongs to closed interval a comma b, right? That function is a non-zero function, and f of x greater than 0. Assume that f of x is greater than 0 for some x belongs to closed interval a comma b. That means the given function is a increasing function. Now, since f is continuous on closed interval a comma b, by maxima and minima theorem, f attains supremum of f at some point on closed interval a comma b. Since f is an increasing function and also f is continuous, by maxima and minima theorem, f has supremum. Let that supremum of f is denoted by supremum f, SUP-f. Now, now f dash of since f dash of x is greater than 0, no, according to our assumption, for some x value belongs to closed interval a comma b, that means it is an increasing function. Supremum of f is also greater than 0. If it is a the function values are always greater than 0, means supremum is always greater than 0. Right? Now, see, as f of a is equal to f of b is equal to 0, as x not equal to a and x not equal to b for all x belongs to open interval a comma b, f is derivable on open interval a comma b. This is also given. That means differentiation of f is possible. That means f dash of exists at the values of x which are lies in between a and b. F dash of x exists since f is differentiable. What is the definition of differentiable? Now we know that suppose f dash of a is equal to, limit x tends to a, f of x minus f of a by x minus a exist and finite, then f is said to be differentiable at x is equal to a, no? Right. Here already given that f is differentiable in open interval a comma b means f dash of x exists. F has maximum at a point x belongs to open interval a comma b and f dash of x exists. By interior and exterior theorem, f dash of x must be equal to 0. Right? Now, no need to prove this interior and extremum theorem. So directly you can write f dash of x is equal to 0. Okay? Now, there is another proof. Just please go through this proof. Another proof for Rolle's theorem. Right? No need to by heart this theorem. No need to by heart this theorem. This just for information purpose, I wrote this. Now, please go through this theorem. Rolle's, another form of Rolle's theorem. Right, I'll explain this theorem in the next video along with mean value theorems. There is a mean value theorem, no? Mean value theorem and another form of Rolle's theorem I'll explain in the next video.